Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at the neutralization of an acid and a base, as well as some acid-base stoichiometry. What we'll start with first, though, is neutralization. So a neutralization would happen if you reacted an acid and a base, and a complete neutralization would happen if the number of moles of the base was equivalent to the number of moles of the acid. If that happened, then what you would make is an ionic salt and water. So I'm going to use probably the most famous kind of strong acid, strong base reaction that would produce a neutralization if we had equal number of moles of acid and base. So the most common acid you'll see as a strong acid is probably hydrochloric acid in most textbooks, etc. And the most common base is going to be sodium hydroxide. Now, if I react these two things, and I kind of follow double replacement reactions from earlier chemistry courses, the two like items would replace one another in this double replacement. So for instance, the hydrogen, which is positive, would swap places with the sodium, which is positive. And so you would produce NaCl aqueous and water liquid. Now, this would be a complete neutralization if the number of moles of this, let's just call it 1 moles per liter, reacts with an equivalent number of moles of the base. Let's call it 1 moles per liter. Because this is a 1 to 1 to 1 to 1 mole ratio. After these things react, there would be none of this left, and therefore I'd only have literally salt water left. Now, we have learned in previous lessons that sodium chloride is neutral. And we also know that pure water is neutral. So the pH here would be 7 because all of these moles would convert into a concentration of 1 moles per liter sodium chloride. And the water really wouldn't have a concentration. It would be now part of the solvent. Now, this would be the double replacement reaction. We could also write this as a net reaction as well. So we have previously worked on writing net ionic equations, and we can do a similar thing here. So for instance, the chloride ion here is aqueous on the left-hand side, and it's aqueous on the right-hand side of the equation. The chloride really isn't participating in any reaction, and so it's a spectator ion. Now, the other one is the sodium ion is staying aqueous with sodium over here, and so the sodium ion is also a spectator, which essentially means they don't do anything in this reaction. What is changing is the hydrogen ion is becoming part of a water molecule, and the hydroxide ion is becoming part of the water molecule. So there is a change there. They're going from ions to atoms covalently bonded in water. So there's kind of two accepted ways to write out the net reaction for this, which would be H plus aqueous, OH minus aqueous, turning into a water. Or we know that a hydrogen ion or acid really is hydronium ion. So I could write it as hydronium ion, hydroxide ion, and then this would make 2 waters, or I could say water plus water. Both of those would be acceptable. So again, these would be acceptable net reactions, whereas the one above would be a double replacement. Now I just want to point this out. In our basic reaction at the top here that says acid plus base makes salt plus water, the salt in this case literally is table salt. But really a salt is really any ionic compound. It doesn't have to be NaCl. It could be a number of other neutral salts that are being produced. So the next thing we're going to talk about is how do you deal with an acid or base spill? How do you neutralize it, and how do you take away, the dangerous aspect of having a strong acid or strong base spilled? Now there's two ways of dealing with it. One of them is absolutely not a neutralization, but it does change the pH if you use enough of it, and that is to simply dilute with water. Now this doesn't actually get rid of the acid. It just decreases its concentration, and if you have enough water, it will adjust the pH by quite a bit. But this wouldn't be used for a big spill on a countertop or anything like that. Generally, what it would be is if I accidentally spilled some strong acid or base down the sink, I could turn on the tap for a long time, really dilute the acid down to the point where it won't damage any of the pipes or anything like that. Realistically, when you're dealing with an acid or base spill, what you would do is you would react it with the opposite, weak. So what I mean by that is, if I spilt a strong acid, I would put a weak base on it to try to neutralize it. If I spilled a strong base, I would put a weak acid onto it. So for instance, if I spilled a large beaker of hydrochloric acid, what I would want to do is use a weak base to try to neutralize it. Okay. The reason for that is if I used a strong base to try to neutralize it, I could actually end up with a base spill. Essentially, I could overcompensate with base. Now it turns into a base spill, and now I got to add acid to turn it back to try to get neutralized, and I could overcompensate again. With weak acids or weak bases, this can be done in a more gradual and safe manner. So for instance, if I was to spill any strong acid, I personally would use baking soda. Baking soda, which also goes by the name sodium bicarbonate, or also by sodium hydrogen carbonate, could be used to neutralize it because it is a weak base. Baking soda is a weak base. So the symbol for it is NaHCO3. And realistically, I don't care about the sodium. What I really care about is the hydrogen carbonate. The hydrogen carbonate is the base. And so essentially what would happen if I put this as a net reaction is the strong acid in the hydrochloric acid, because H3O plus is strong acid, would react with the HCO3 minus. It would donate its hydrogen there. This would then become water, which is neutral, plus carbonic acid, which is H2CO3, which is a weak acid. And to be honest with you, this actually breaks down into water, which is neutral, and carbon dioxide gas. So realistically, it would take care of that spill. If I overdo it with baking soda, then I have a baking soda spill, and it's not a big deal. I can sweep it up, because I would generally use, solid baking soda. I would pour it all over the solution that had spilled. It would start to bubble, create carbon dioxide, etc. Now, something else that we do in the lab to actually help with this, with an acid spill and an acid spill kit, is we put kitty litter in it. So if I mix a whole bunch of baking soda and kitty litter, the baking soda actually neutralizes the HCl, and the kitty litter soaks it all up, and then you can sweep it up rather than using paper towels. So that's something a lot of labs would have as well. Now, if I was to spill a large beaker of sodium hydroxide, what I would want to use is a weak acid. Now, a lot of weak acids are in liquid form, and I can use that, but I could also use some weak acids that are in solid form. So I've heard of using citric acid, which you can buy as a solid, dumping that on top of it, and same idea, kitty litter in there to soak it all up. So the key thing is, whenever we're really dealing with a spill, not just something poured down the sink, what we want to do is react the strong acid with a weak base, Probably the most common would be sodium bicarbonate or baking soda. And if I spill a strong base, I would want to use a weak acid to neutralize it. There's lots of options out there. I just pick citric acid because you can buy it as a solid and dump the solid right on top of the liquid base, and then that would neutralize it. The next thing we're going to look at is just doing a little bit of acid-base stoichiometry, which will allow us to do some calculations when we get to titrations in our next lesson. So, acid-base stoichiometry is really using mole ratios in an acid-base reaction to figure out either usually a volume or concentration of acid or base required to neutralize the other thing. So let's look at this first question here. It says calculate the volume of 0.50 moles per liter sodium hydroxide required to neutralize. So we want it to be completely neutralizing 10 mils of 0.2 molar HNO3. So the first thing, of course, we have to start with is a balanced chemical reaction. So sodium hydroxide plus HNO3. Now I'm going to do a traditional double replacement reaction here, and in this double replacement reaction, we're looking at sodium to swap out with hydrogen because they're both positively charged in these compounds. So that's going to make sodium nitrate, which again, this is 100% neutral. It's a group 1 metal with the conjugate of a strong acid. And then, of course, H is going to be with OH, and I could write that as HOH or H2O, whichever one you're more comfortable with. It really doesn't matter. Now, because this is a monoprotic acid and this is a monoprotic base, we'll notice that the balancing works out to being 1, 1, 1, and 1. So there's our first kind of major step, get our balanced chemical reaction done. The next thing I like to do is write out all the information I'm missing as well as all the information I'm being given. So it says calculate the volume of NaOH. That's going to be my goal, so I'm going to write that there. And I've been given the concentration of it, which is 0.50 moles per liter. And I've also been given the volume of the nitric acid as being 10 milliliters. Now I'm going to convert that into liters right away. So that's 10 milliliters in liters with the significant digits they've given us. They've also given us a concentration of 0.20 moles per liter. Now, we got to remember in stoichiometry, we're always trying to figure out moles or to convert moles of one substance into moles of another. So I can see that I could calculate the number of moles of nitric acid. And once I did that, I could do a mole to mole ratio to sodium hydroxide. So we traditionally would be using C is equal to N over V, and then, getting moles by going C times V. And we're going to do that. But I'm not going to use an equation. I'm just going to use unit analysis. It's the same thing, just in a different presentation. So again, step number 1, I'm going to convert the volume and concentration into moles. Step number 2, I'm going to do a mole to mole ratio to get the moles of sodium hydroxide. And once that's done, then I can take these moles and the concentration, and I could calculate a volume in a third step. So what should I start with? I always want to start with the number that has a single unit, like grams, or in this case, liters. So I'm going to start with 0.01000 liters of nitric acid. And I want to get rid of that, so it's going to go on the bottom of my next fraction. So for every 1 liter, there is 0.20 moles of nitric acid. And so the unit of liters would cancel, and I have moles of nitric acid, which is right there. So this is step number 1. Step number 2 is to do a mole to mole ratio. So whatever moles I want is on top. I want the moles of sodium hydroxide, so I'm putting that on top. I want to get rid of the moles of nitric acid, so I'm going to put that on the bottom. I go to their coefficients, it's 1 and 1, and so I put those in. Now, if you're thinking to yourself, if I have a 1-to-1 ratio, do I really need to show this? And the answer is yes. This is a conversion. It's a conversion of units, and it requires work to be there. So this would be step number 2, and the unit of moles of nitric acid would cancel out with moles of nitric acid. Now my final answer I want is in liters. But what I need to do is get rid of the moles of sodium hydroxide, so I'm going to have to put that on the bottom. Well, liters and moles, that is a concentration. This is just inverted. So it's for every 1 liter, I have 0.50 moles of sodium hydroxide, which is this concentration, just inverted. The moles of sodium hydroxide cancel out with the moles of sodium hydroxide, and I'm left with liters of sodium hydroxide. So this would be step number 3. So all I'm going to do is take everything on the numerator in one set of brackets, hit divide, everything on the bottom in one set of brackets, and hit equals. When I type that in my calculator, I get a volume of 0.004 liters. Now, if I was to do this in correct significant digits, I could do this a couple of different ways. I could say it's 0.0040 liters. I could say it's 4.0 times 10 to the negative 3 liters. Or I could say it's 4.0 milliliters. All of those mean the exact same thing. I'm just showing it in a different way, and they're all to 2 significant digits because 0.50 is 2, 0.20 is 2, the 10.00 is 4, so I want to use the lowest number of significant digits, which is 2. In this next question, we are really going to look at a diprotic strong acid reacting with a monoprotic strong base. So our ratio won't be 1:1 anymore, so it's going to be a little bit different. The other thing that's different about this question is we're going to calculate a concentration rather than a volume, so the last step is going to look a little bit different as well. So the question says, calculate the concentration of a 15 milliliter potassium hydroxide solution if 8.75 milliliters of a 0.55 moles per liter H2SO4 solution was required to completely react with the KOH. So let's start with the double replacement reaction. So we have H2SO4 aqueous, and it's reacting with potassium hydroxide, aqueous. Like replaces like, so the positive hydrogen is going to replace the spot with the positive K. So we're going to end up having K2SO4 aqueous. I know this is aqueous because a group 1 metal cation with anything is going to be soluble. And then I'm going to write this as HOH, so I can see that that's the OH and this is the H. It allows me to better understand what to do when I'm balancing. So I need to have 2 hydrogens, which means I have to have 2 hydroxides, which means I have to have 2 Ks, and now everything should be balanced out nicely. The next thing I'm going to do is just write down everything I know and don't know. So I don't know the concentration of KOH. That's what I'm working towards. The volume is 0.01500 liters. That's 15 milliliters. And in order to figure out the concentration, I am going to need the moles. Now, on the other side here, I do have the concentration of H2SO4. It's 0.55 moles per liter. The volume here is going to be 0.00875 liters. That is the 8.75 milliliters. And from there, I'll be able to figure out the moles. So my first step will be to get the moles of H2SO4. My second step will be to convert that into moles of KOH. And in the third step, I'm going to turn that into a concentration. So again, I always want to start with my number that has a single unit in it, like liters or grams. In this case, it would be liters. So I'd be 0.00875 liters. I want to get rid of liters and I want to get moles, so liters has to go on the bottom to cancel out. What I want needs to go on top, so I want moles of H2SO4. So there is 0.55 moles for every 1 liter. That's simply the concentration, and step 1 is done. So again, the liters cancels out with the liters. In my next step, I need to do a mole-to-mole ratio, the moles of what I want on top. So it's moles of KOH on top. and it was moles of H2SO4 on the bottom. And I'm just putting in my coefficients here. So it would be 2 on top for the KOH, 1 on the bottom for the H2SO4. So this would be step number 2, my mole to mole ratio. In my third step, I need to turn this into moles per liter. Now, I already have moles of KOH, so normally we're quite used to canceling out what's on top with something on the bottom, but I actually don't want to cancel out this unit. I just want to divide it by the number of liters, which I have, which is that 15 milliliters, so 0.01500. So then the question often becomes, well, what do I put on top here? And the answer is just 1, okay? So if I multiply by something, by 1 over something, that's the same as division. And that's exactly what I'm doing here. So I'm not canceling out the moles of potassium hydroxide because I want moles of potassium hydroxide per liter. And in order to make it per liter, I'm really multiplying by 1 over, which is the same thing as division. And so this would be my third step where no unit cancels in this last part here. All right, so everything on top in one set of brackets, you hit divide. Everything on the bottom in one set of brackets, you hit equals. Now, if you do that, you should get a concentration of 0.6416 moles per liter. Now, what I'm going to do is check for my significant digits. I've got 4 significant digits there. I have 3 here, I have 2 there. So I need to get this down to 2 significant digits. The 0 in front doesn't count, so I underline the 64. Circle the 1 behind it. The 1 does not round up the 4. So my final answer would be a concentration of 0.64 moles per liter. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.